Alright, so we will start with the many electron problem, or in general quantum many particle problem. So, we have revised up to the basic quantum mechanics and the exactly solvable problems, particle in a box, harmonic oscillator, as well as hydrogen atom. Okay. And we kind of said that if you go for more than one electron which are interacting, then the problem is not exactly solvable, and the solutions are usually done through some approximations. And two important approximations that we mentioned are variation method and perturbation theory. We have done that in the previous class, but we will again redo this variation and perturbation in this class as well. But unlike the last class where I actually presented variation and perturbation back to back, here I will present this as and when required. So, first probably variation and then perturbation when is required. We will also, I will also tell you the symbols, because at this point we have to be very consistent in the symbols. Symbols that we will use, we will try to be consistent as much as possible. There will be some points where there may be problem, but we will introduce the symbols. So, first of all, we want to talk of many electron problem. When we are saying many electron problem, they are by definition interacting many electron problems, because if they are non-interacting, of course, the problem is nothing but sum of one particle problem, as we noticed. So, first is a trivial case of a many electron problem, where the electrons or the particles are not interacting with each other, right. This is something that we have already discussed, but this is also a part of many electron problem, but they are non-interacting and hence their solutions are trivial. So, what is what is non-interacting? That your Hamiltonian for n particle problem is a sum of n one particle problem. So, H1 plus H2 plus Hn. Okay. Let us say that your Hamiltonian is of this form. In this case, the results are very easy. The total wave function is a product, and we will later see actually this will be an antisymmetrized product. Of the spin orbitals which are eigenfunctions of the one particle operator H. Okay. So, it is very easy. So, basically you have to solve only one particle problem. It may also happen that this H and this H may be different. So, it may be H1, H2, H3. Even in that case, the problem is trivial. Okay. So, you have to simply solve H1, H2, etc., and then later on make an antisymmetric product. So, we will see. So, this is an easy thing, and the energy or the eigenvalue of the n particle problem or the n electron problem is simply a sum of n one particle eigenvalues. So, basically solve this one particle problem, you will get an eigenfunction whose products is the total eigenfunction of this Hamiltonian, and this eigenvalue sum is the total sum of this n electron problem. So, this is a trivial problem. So, this is really not called a many electron problem, because this is actually one particle problem. It is just that from the one particle problem you can construct the n particle problem by trivial product and sum. So, when we will talk of many electron problem henceforth, it essentially means that it is an interacting many electron problem and not non-interacting, which means the Hamiltonian cannot be written in this form, okay, as a sum of n one particle Hamiltonian. So, those are the problems which are of interest, because they cannot be now trivially solved by solving the one particle problems. Like this problem can be solved trivially, as long as you can solve the one particle problem, you can solve the n particle problem. So, let us say, let us look at now the interacting problem. So, we actually discussed it last time. So, we have an interacting many particle problem where the Hamiltonian has a form of this kind. It will still have a one particle term. So, I am just writing this as sum of I equal to 1 to n, where H is again a one particle operator, just like this. So, I am now writing as a sum, plus it has an additional term which is usually for the Coulomb problem written as I less than j 1 by Rij, where Rij is the distance between the electrons I and j, the coordinates of the electron I and j, right. So, Rij is nothing but the distance between Ri and Rj. This is an interacting problem, because now this problem cannot be written as a sum of n one particle problem, simply because as I told you, this term cannot be written as a sum of one particle Hamiltonians, the 1 by Rij term. So, essentially for two particle, it will be H1 plus H2 plus 1 by R12. That 1 by R12, which is the Coulomb operator, cannot be split as sum of two one particle operators. Hence, this theorem cannot be used. Okay. So, you cannot simply get the eigenvalue and eigenfunction of this problem by solving one particle equations. So, this is a difficult problem, and in principle the solution, when I mean by solution is eigenvalue solution, eigenvalue equation for this Hamiltonian. In principle, the solution is not the exact solution, I should say the exact solution cannot be found. So, any method that we will propagate in this course will be approximate in nature. So, that is the first very important point to realize, that nothing that we will speak is exact. What is important is, however, to understand how to get the exact solution, or how to reach towards the exact solution, which means how to improve the solutions, one approximation to another approximation, how the approximations is progressively improved. I think that is very important to understand. Otherwise, of course, the theories that we will develop will have no meaning. So, that is what we will do. Before we do that, let us first try to look at some important symmetry of this problem. So, let us say that I write a two particle problem as an example, as H of 1 plus H of 2 plus 1 by R12. So, very simple two particle problem, which can now be written as sum of two one particle Hamiltonians, H of 1 and H of 2 plus 1 by R12, which means essentially only one term of this summation, because there is only one term for two particle problem. So, first to note that if I interchange the two particles, the coordinates of the two particles, so write this H of 2 1, then it is identical to H of 1 2. Okay, because R21, if I interchange 1 and 2, R21 is exactly same as R12. And of course, H of 1 plus H of 2 will remain invariant. So, just a question of writing H of 1 plus H of 2 or H of 2 plus H of 1. So, the point is that the R12 and R21, each of them represents the distance between coordinates of 1 and coordinates of 2, and this distance is invariant, whether I call it 1 to 2 or 2 to 1. Hence, the entire Hamiltonian is invariant if I interchange 1 and 2. This is usually called the permutation invariance. So, the Hamiltonian is permutation invariant. Okay. So, this is an important point for any n particle problem, whether they are non-interacting or interact. Of course, if it is non-interacting, this is trivial. Okay. If it is interacting also, the interactions are of the kind which are basically permutation invariant. All right. So, if you recognize this, then we can right away do some analysis based on this symmetry and come to some conclusion. So, that is what we will first do, because that is a very general conclusion that we will have. So, we will first try to analyze this problem, that in case of permutation invariance, what do you get? So, let us try to understand the word permutation little bit more carefully. So, again I will take an example of a two particle problem. So, permutation is an operator, let us say P of 1 2. So, permutation itself, I have defined a new operator called permutation operator. It is a two particle permutation operator P1 2, it can be P2 3, P3 4, does not matter, that depends on where it is acting. So, if it acts on a function, two particle function 1 2, then it generates a new function which is phi of 2 1. Remember, this is not a Hamiltonian, it is acting on a function. So, if it acts on a function phi 1 2, the definition that it generates another function where 1 is replaced by 2, 2 is replaced by 1. Okay. So, I hope it is clear what this function means. So, you can take some example of a function which is a function of coordinates of 1 and 2, which are actually, I told you these coordinates are essentially space and spin coordinates, that you should not forget, 4-dimensional coordinates, but you can take any other function. So, if you have for example a two particle function sine of x1 into exponential minus x2, let us say I have a function f of x of x1 x2. So, what will this permutation operator do? It will generate sine of x2 e to the minus x1, right. It will simply change x1 to x2. So, this will now be actually a space spin coordinates in our case, but whatever it is, if it is space coordinate, it will simply change space, spin coordinate, it will simply change spin. So, it will simply make x1 to x2, x2 to x1, right. So, this will generate another function. Now, this function of course may not be equal to this function or may be equal, that depends on the nature of the function. If the nature of the function itself is such that it is permutation invariant, then of course it will generate the same function. Remember, this is a function. Permutation invariance that I talked about is for the operator. Now, I am saying in any arbitrary function, if an operator acts on that function, it changes. Just like we defined for the harmonic oscillator parity operator, where parity operator acts on a function, it changes x to minus x, the coordinate for one particle problem. Very similar we are defining here, they are not making it negative, they are simply interchanging. So, this actually interchanges the coordinates of the two particles. Okay. So, that is why I call it permutation operator. Then we notice that for such a permutation operator, if you have the product of the Hamiltonian, n particle Hamiltonian or n electron Hamiltonian with H and P acting on an arbitrary function phi 1 2. So, this is for any function phi. I hope all of you understand this symbol, it is an arbitrary function. So, any function phi, if I allow this to act, then let us see what happens is that first P12 will act on phi 1 2, because P12 can act on whatever is on the right of this. So, this will make it H of 1 2 phi of 2 1, right. H of 1 2 will remain, that is an operator, and this acting on phi of 1 2 will make it phi of 2 1 by my definition, correct. Is it okay? Then I allow the reverse to act, P of 1 2 H of 1 2 phi of 1 2. So, basically this operator is acting on phi of 1 2 or this operator is acting on phi of 1 2. So, I am just analyzing these two. When this operator acts on phi 1 2, note that the P12 now acts on this combination of H12 phi 1 2, whatever is on the right of P12. So, what will it generate? It will generate Now 1 will become 2, 2 will become 1. So, it will generate H of 2 1 and phi of 2 1, correct. So, both the coordinates of 1 and 2, sorry, both the coordinates of 1 and 2 are interchanged in the Hamiltonian as well as on the phi. Okay. So, both of them will be interchanged, and here only one of them has been interchanged, the other has remained as it is. However, now we note, because of the permutation invariant, this H of 1 2 is nothing but H of 2 1. All right. So, this can be further written as H of 1 2 phi of 2 1, or this can be written as H of 2 1 phi of 2 1. The point to note is that both of them are identical. Okay. Is it clear? So, if I have HP acting on any function or PH acting on any function, the result is identical. Okay. Because simply because of this permutation invariant. These functions are different. Of course, phi 1 2 is different from phi 2 1, because that is an arbitrary function. This may or may not be same, but the results is different simply because the results are the same simply because H of 1 2 is equal to H of 2 1. So, with that we can now note that if this is true for any arbitrary function phi, what does it mean? That this operator is identical to this operator. I hope all of you remember operator equality. When A is equal to B, if A acts on any function phi and gives you equal to B acting on any function phi, I mean the same function of course, okay, for any arbitrary function A phi equal to B phi, then A is equal to B. Remember, operator equality is a very strict equality. So, if A acts on a function and B acts on the same function on a given function, they are equal. It does not mean that the operators are equal, correct. So, the operators are equal only if A acts on a phi and B acts on the same phi for all arbitrary phi. If this is equal, then we say A equal to B, correct. So, that is very important. This again, please understand this symbol, arbitrary phi, any phi. But if it is true only for a set of phi, then it is not necessarily true. The same goes for the null operator. So, if for example, if A phi is 0 for all arbitrary phi, then A is a null operator. Null operator is 0 operator. So, there are certain rules. So, here also it is the same, A minus B acting on phi is 0. So, A minus B is a null operator, which means A is equal to B, correct. So, it comes exactly from the same. So, now we can argue from this that HP, so we can now say that the operator HP is same as the operator PH. Correct, which means that the two operators commute with each other. And then the rest of the argument on symmetry will fall on the same lines that we did for the parity operator, very similar argument. So, what is the next argument? The argument is that instead of looking for the eigenfunction of the Hamiltonian, we will now look at the eigenfunction of the permutation operator, because they commute, and the theorem of quantum mechanics says that if two operators commute, they have common eigenfunctions, right. They share simultaneously the same eigenfunctions. Hence, instead of looking for the eigenfunction of the Hamiltonian, we look for the eigenfunction of the permutation operator. This is basically also the objective of the group theory, that in group theory we try to identify symmetry operators which are commute to the Hamiltonian, and then we analyze the eigenfunction of the Hamiltonian in terms of the eigenfunctions of the symmetry operators. So, then we get the symmetry properties of the wave function. So, exactly the same argument we will use here, and the same thing we did for the parity operator. So, we will now look for the eigenfunction of the permutation operator, and let us see how they will look like. So, that will give us a clue on the eigenfunction of the two particle wave function. So, let us now look at
the eigenfunctions of the permutation operator. So, how will it look like? So, let us say that I write the eigenfunction of the permutation operator as P12 acting on psi12 equal to lambda times psi12. Remember, now this is not an arbitrary function. This psi is not an arbitrary function. This is an eigenfunction of the permutation operator. So, just note this. Okay. This psi is an eigenfunction, hence I am saying that the operator acting on psi of 1 2 gives you a number times psi of 1 2. So, that is the eigenvalue equation, right. Operator acting on a function gives you a number times the function. This is the eigenvalue, this function is the eigenfunction, right. So, we know this. So, we want to analyze this. The reason we are analyzing this, that we know that this psi will also be an eigenfunction of the Hamiltonian because of this commutation rule, right. So, let us see how this looks like. So, to analyze this, let us apply exactly like we did for the parity operator. In the parity operator case, apply this operator twice on this. So, let us analyze this equation, P12 acting on psi12 and another P12 acting from the left. So, what will it give? If you look at the eigenvalue equation, this gives you lambda times psi12, right. Lambda is a number, so it can be taken out. So, then P12 will again act on psi12 to give you another lambda times psi12. So, the result will become lambda square psi12. Is it clear to everybody? Because the eigenvalue equation is repeated twice. In fact, all of you know that if A psi equal to lambda psi, A to the power n psi equal to lambda to the power n psi. Okay. So, any power of that operator also has the same eigenvalue, eigenfunctions, not eigenvalues. Eigenvalues are going to be the power, eigenfunctions are same. So, you have a lambda square psi 1. On the other hand, if I analyze the left hand side, by definition, you remember if P12 acts on psi12, they become psi21 for any arbitrary function. So, it will be true for eigenfunction as well. Then P12 again acts on psi21, it will bring it back to psi12. Right. So, if you analyze this, then I get psi12 is equal to lambda square psi12, right. So, this is equal to lambda square psi12 and the left hand side is equal to psi12 itself. So, then trivially I get a result that for all eigenfunctions of the permutation operator, the eigenfunction is the eigenvalue square times the eigenfunction again. And that gives me a handle to get the value of lambda, because now I know that from here lambda square is equal to 1 and hence lambda is either plus or minus 1. Okay. So, I get the eigenvalue for this result. Then what do? I go back to this equation again. So, I write P12 psi12 and now I put the eigenvalue is equal to plus or minus psi12, correct. Plus minus 1 means plus or minus psi12, just multiply plus 1 minus 1 and then apply the definition again on the left hand side, the definition. So, by the definition, this is psi21 equal to plus or minus psi1. So, we get an interesting result for the eigenfunction of the Hamiltonian or the eigenfunction of the permutation operator. What is that interesting result? That if I permute the coordinates of the two particles 1 and 2, the eigenfunction will either remain the same or change sign. So, that is the result that we get. In fact, this result is generally true for not only electrons, but in general for all quantum particles, because remember we have not used anything about electrons in this definition. For all quantum particles, the Hamiltonian permutes with the permutation operator simply because the quantum particles are indistinguishable. So, this really comes from the fact that the quantum particles are indistinguishable. So, I can't distinguish between 1 and 2. So, that is the reason this permutation invariance come. So, this result is a very general result of quantum mechanics, that all quantum particles follow or obey a rule that if I interchange the coordinates of the electrons or the particles, they will be either positive for the particles or the negative in the sign. So, this is called the symmetric properties with respect to permutation for quantum particles. So, then without any further proof, we mention that if it is symmetric, which means if it is plus, okay, then symmetric with respect to interchange of the coordinates, then these are called the Bose particles, which are called the bosons, and they follow the very famous Bose-Einstein statistics. And those which are antisymmetric, which essentially means the negative sign here, are the fermions, which obey the Fermi-Dirac statistics, right. So, there are two very important statistics in quantum mechanics. So, for our case, so for electrons, again we have mentioned this in the last class also, the last course also, that the electrons are fermions, they obey the Fermi-Dirac statistics. So, for the moment we will not worry about, for this course we will not worry about the plus sign, we will only worry about the minus sign. So, essentially it means that all the wave functions that we will construct for the Hamiltonian from now on must be antisymmetric with respect to interchange of the coordinates of two particles. Note that this result, although I derived only for two particles, this result is general for any n particle. So, for any n particle function, if I interchange the coordinates of two particles, any two particles, the wave function will be antisymmetric with respect to the permutation of those two particles. So, every pair interchange should produce a negative sign. That is important thing that we should remember. So, if you now look at our theorems, even for non-interacting theorem, I said that the wave function is a product of the one electron eigenfunctions, right. So, now we can see that a product is not acceptable unless it is antisymmetric. So, that is the reason I wrote in bracket, if you remember, antisymmetrized product. Okay. So, the product by itself is not acceptable unless it is antisymmetric. So, all electron wave functions must be antisymmetric, even if they are non-interacting or interacting. Okay. So, any time we talk of a product, remember that they have to be antisymmetrized product. Okay. Many times this antisymmetric is actually called antisymmetrized. Okay. So, how do I make this product? To do this, first again let me go back to the exact case. Exact case is the non-interacting n particle problem or n electron problem. So, from now on we will only talk of n electron, and that is the whole subject today, that the symmetry of the many electron problem. So, let us now go back to the n electron non-interacting problem. So, let us again concentrate on a two particle problem, because two particle problems are very instructive. Okay, two particle non-interactive, very instructive because they give you all the physics that is required and they are simple to analyze. Okay. So, my Hamiltonian now is just h of 1 plus h of 2, right. It is very simple, I do not have any interacting term. So, this is a two particle non-interacting Hamiltonian. So, I have h of 1 plus h of 2. Then what did I say? The eigenfunction of this is just a product of or antisymmetrized product of the eigenfunction of these two. So, let us now write down the eigenfunction of this. Note that